Good morning. I'm Glenn Vanderburg. I work for InfoEther with Rich Kilmer and Chad Fowler and Bruce Williams, who I suspect a lot of you know here. I'm here to talk about real software engineering. I've been at all 4 of the Lone Star RubyConfs and really enjoy them. So to start off with, software engineering doesn't work. At least as it's currently taught in universities and in training programs at companies, if you happen to work for one of the few companies that cares about teaching such things. The techniques that are taught and that are called software engineering simply don't work. They don't reliably control costs. They don't reliably produce quality software. Sometimes, even when they're practiced rigorously by people who've been trained to do so, they don't produce working software at all. And that shouldn't really be surprising to any of us because this seems to be common knowledge among working programmers all over this country at least. But while it's not surprising, it is odd. Because in every other field that aspires to the title of an engineering discipline, the term engineering is reserved for practices that work. In fact, that's as good a capsule definition of engineering independent of any particular discipline that as you're likely to find, which is the set of practices and techniques that have been determined to work reliably through experience. And yet in software, we have this set of practices that don't work, and we call that engineering. Now, this has caused a lot of discussion, especially over the past year or so, about whether software is really an engineering discipline at all, and whether software development really doesn't fit that metaphor. It's not engineering, it's more a craft or an art or something else, or gardening or movie making or various different analogies I've heard. And maybe engineering is just an inappropriate metaphor for the task of building software. And I don't think that's true. I do think software is an art, I do think it's a craft, and I do think it is in some respects a science, but that doesn't mean it can't also be engineering. And I say that the problem is that the people who have defined the set of disciplines that we call software engineering have misunderstood 2 very important things: software and engineering. And that has resulted in software engineering being actually a caricature of an engineering discipline. So I'm going to explain what I mean by this. And to do so, I need to first start off by explaining what I mean when I say that software is a caricature of engineering and kind of how it got to be that way. And then I need to explain what real engineering looks like. How many people in the room were trained as engineers, not as software developers? Okay, interesting. I'm especially interested in feedback from people who have more of a classical engineering background, because I don't. I've had to kind of learn all this on my own. But I think I've come to a pretty good understanding of where software engineering got it wrong. And then we're going to look at what real software development looks like. And in the middle somewhere, I think we can develop a picture of what real software engineering is. So the first time that the term software engineering really got bandied about a lot was in 1968 at a conference in Garmisch, Germany, organized by NATO, of all things. The first conference on software engineering, sponsored by the NATO Science Committee. And at this time, people were dealing with what was called the software crisis, and software projects were really unreliable and flaky and error prone and failure prone and had huge cost overruns, and they really didn't know much about how to manage them. And so they said, we need to kind of grow up as a discipline and as a field and start becoming an engineering discipline. And so they had this conference. And I've known about and heard about this conference for many, many years, and never really knew any details about it. And so as I got interested in this topic, I went and read the proceedings, which are all online, and I was expecting to find, okay, this is where the madness started. And in fact, no, I didn't find that at all. The participants in this conference were, by and large, really smart people who were working software developers. There were a few academics, but the academics had good things to say as well. And by and large, the findings of this conference were entirely reasonable and reflected a great deal of wisdom about software and its state at the time. In fact, mostly what you'll be impressed by is, as you go there and read those proceedings, if you do, is how willing they were to admit that they didn't know anything. The conference is full of we're just kind of babes in the woods at this. It's a new field. It's different from other fields before. There's all kinds of stuff we don't know. We kind of think it might be like this. There was a lot of uncertainty. And Alan Perlis gave a talk in which he's at the end of the conference, in which he sort of summarized the few things that the group was able to all agree on about what software as engineering should look like. And the first of the three things were, a software system can best be designed if the testing is interlaced with the designing instead of being used after the design. That's pretty reasonable by our standards. Number two, a simulation which matches the requirements contains the control which organizes the design of the system. Now, the terminology has evolved since then, and so that doesn't immediately seem to make a lot of sense. But I think if you combine that with the third one, it is clear what he means. Through successive repetitions of this process of interlaced testing and design, the model ultimately becomes the software system itself. In effect, the testing and the replacement of simulations with modules that are deeper and more detailed goes on with the simulation model controlling the place and order in which these things are done. He was talking about unit testing and mocking and iterative design and development. Pretty reasonable. There was a second NATO software engineering conference a year later. The tone of those proceedings are entirely different. During that year, everything went wrong. Within that year, software engineering turned into what it was for many, many years, which is an entire field of processes designed in academia for practitioners. What went wrong in 1 year? Well, I don't know. I was alive then, but I wasn't a computer programmer back then, and so I wasn't involved in these processes. But I have a theory about what went wrong, and I can illustrate that theory by talking about another place where some very reasonable statements were misconstrued and turned into completely unreasonable conclusions, where we know what happened, and that is the birth of the waterfall process. Waterfall was introduced by Winston Royce in a paper at IEEE WestCon in 1970. And the paper was called Managing the Development of Large Software Systems. And Royce spent the rest of his career running around saying, no, I didn't mean that. I was misquoted. I've heard that story too. And when I went back and read this paper, I was astonished to find, I wasn't surprised to find that he was telling the truth. He really didn't recommend waterfall. But what I realized was that the problem, the reason that people thought he was recommending waterfall is that this paper is a marvel of bad information design. If you wanted to study how to write a paper that conveys exactly the opposite impression from what you're trying to get across, you couldn't do better than to go read this paper. So let's take a look at this for a minute and assume that you're a manager of a group producing software in 1970, and you're struggling with how to reliably estimate and produce stuff that works and all these problems that have plagued software management since the beginning. And a friend or colleague or maybe one of your employees drops this paper on your desk and says, this might help. Oh, managing the development of large software systems. That's pretty good. That's what I'm interested in. And I see that there's a diagram there on the front page. So, let's start by kind of looking at the diagrams and see what this is about. Skim it first and then read. So that diagram says, you start with analysis and then you go to coding. And that's kind of simplistic. And even I know that's kind of simplistic. And so before I waste time reading this paper, I'm going to look at the rest of the diagrams and see if this guy has a brain in his head or not. And so at the top of the second page, I see this. This is the first time the classic waterfall diagram ever appeared. And, wow, that's pretty good. System requirements, and from that you get software requirements, and then you move to analysis and design and coding and testing and operations. And look at the caption there. Implementation steps to develop a large computer program for delivery to a customer. I can understand that process. That makes sense to me. I see how all those things work. And I got this meeting to go to. I got what I need out of that. Look at the very next line. I believe in this concept, but the implementation described above is risky and invites failure. The funny thing is that sentence describes figure 3, which is on the next page. To find out what Winston Royce has to say about figure 2, you have to go back to the first page where he says, an implementation plan keyed only to these steps is doomed. Well, let's be optimistic and assume that the manager comes back from his meeting and picks up the paper again and tries to continue through it. And he flips to the third page and he sees this. Okay. To our eyes, that looks a little more reasonable. We can see feedback coming from later steps to influence earlier steps as you learn more, as you get down into the details. And then Royce goes on to say that the feedback isn't even that localized, and sometimes, the things you learn in testing have to go all the way back up and affect the software requirements. And this is starting to seem confusing and messy and hard to control. And whoa, and I don't know what this means, and all these blank boxes, and it just gets worse and worse. And then the final diagram, which is helpfully labeled summary. Summary, there you go. I think I'll go back to that one. And within just a few years, waterfall was an established standard in the industry. And it's easy to kick waterfall, and it's kind of, most people have realized that's not the way to do things. But I've run into groups that kind of religiously follow waterfall and don't see how anything else could possibly work as recently as 3 or 4 years ago. And as recently as the late 90s, the Department of Defense was still essentially mandating waterfall for all of the projects that they paid for. It has taken a long time for this idea, which was presented as a way of doing things that was obviously doomed, to finally sort of work its way out of people's consciousness. Because people like simple solutions, and they hear terms and map those terms to things they already understand or think they understand, and latch onto that and run with it without thinking very carefully. That's just a characteristic of people. And it happened with waterfall, and I think it also happened with this term software engineering. H.L. Mencken said, "For every complex problem, there is a solution that is simple, neat, and wrong." And that certainly applies there.